Welcome to Numerical Methods for Scientists and Engineers. Video 1. Linear Systems. Iterative Methods. Basics of Iterative Methods. Solving large linear systems by direct methods requires very large memory storage space and leads to excessive computation time. Iterative methods avoid computation with zeros. In Figure A and B below, two-banded linear systems with 5 or 7 diagonals consisting of mostly non-zero elements are depicted. The rest of the elements are zero. These matrices are encountered as a result of discretizing 2- and 3-dimensional elliptic partial differential equations in regular domains. The sparse matrices observed when discretizing 2- and 3-dimensional elliptic partial differential equations in non-regular domains are shown in figures C and D. Consider the following system of n equations with n unknowns, which can be expressed as a matrix equation, A times x equals B. Steps of an iterative method includes initialization, computation, and termination. The first step in every iteration process is to make a suitable initial guess for the solution. An arbitrary initial guess is often set for the values of unknowns due to simplicity and ease of implementation. Linear systems of equations are not very sensitive to the initial guess, but nonlinear systems are. In nonlinear systems, an initial guess in close proximity to the solution, so-called the smart guess, speeds up the iteration process considerably. The computation step involves the way current estimates are computed, that is, how the current estimate is computed. A suitable iterative scheme, which is expressed mathematically by the following general equation, is implemented. This step is the core of an iterative algorithm, and it is different for each iterative method. An iterative procedure is terminated basically for two reasons. 1. When a current estimate converges to a solution within a predetermined tolerance. This step is crucial to finding a quick solution while avoiding oversolving. Successive approximations of a converging iterative system will approach closer to the true solution with each subsequent iteration. Since the true solution x is unknown, it is impossible to verify how close the pth estimate is to x. An iteration process is terminated when the current and prior estimates are sufficiently close to meet a preset convergence tolerance or stopping criterion. The stopping criterion, epsilon, determines the level of accuracy sought in the solution and also affects the computation time. Commonly used stopping criteria are based on the absolute error of the displacement vector at the pth iteration step. The displacement vector is defined as the difference between the estimates obtained in two consecutive iteration steps. There are basically 3 absolute error termination criteria based on L1 norm, L2 norm, and L-infinity norm. Here, epsilon 1, epsilon 2, and epsilon 3 are suitable absolute convergence tolerances, and n denotes the number of unknowns. The 3 most commonly used relative error termination criteria are based on L1 norm, L2 norm, and L-infinity norm. Here, epsilon 1, epsilon 2, and epsilon 3 are suitable relative convergence tolerances. 2. When the number of iterations reaches a predetermined upper bound, maxit. We do not know in advance whether convergence with the desired tolerance can be achieved within a predetermined number of iterations. In the event that a system converges slowly or does not converge at all, the iteration process will go into an infinite loop unless the loop is terminated. It is a programming practice to set an upper bound maxit for the maximum number of iterations permitted. There are basically two sources of error in iterative methods as applied to systems of linear equations: truncation error and round-off error. All iterative methods are subjected to truncation as an iteration process eventually should be terminated after a finite number of iterations. In practice, it is impractical to perform an infinite number of iterations in an attempt to find the true solution, which is unknown. Accordingly, an iterative solution of a linear system is inevitably approximate. However, the truncation or approximation error can be reduced by applying a smaller convergence tolerance, which in turn yields an increase in the number of iterations. The round-off error is introduced when computing iterates over many iteration steps. In direct methods, a round-off error in the value of the last unknown propagates at every step of the solution, corrupting the values of the remaining unknowns. The round-off error in an iterative method is an error that occurs only in the last iteration step. Because the coefficient matrix is always intact throughout the iteration process, and the current estimates are always computed from scratch at each iteration using prior estimates as the initial guess vector. In an iterative processes, the magnitude of round-off error is usually not considered serious, except for ill-conditioned systems, because the truncation error introduced by terminating the iteration is generally larger. In this context, the round-off errors are less serious problem in iterative methods than in direct methods. Furthermore, the following factors make iterative methods less sensitive to round-off errors. Iterative methods are employed for diagonally dominant systems, which reduces the influence of round-off errors. The more dominant the system, the less the round-off error. The systems of equations dealt with are generally sparse, and the presence of the zeros may remove the influence of some of the previous components. That is all for now. See you next time with another topic. Bye.